a hemisphere and there you go, and a cylinder. Okay, so here's my hemisphere, which is half of a sphere. And then here's my cylinder. Cool. But when you put two shapes together, especially 3D shapes like these, what happens is, remember, surface area is like if you are wrapping a present. Let's say this is a trash can and you're gonna wrap it up and give it to someone as a present. That would be a horrible present. But actually, guys, trash cans are like really expensive. This is such a weird random thing, but when I was buying a trash can for my new apartment, it was like $50. I was like, what? How is this $50? Anyways, I would have accepted a present of that was a trash can, honestly. But anyways, we are wrapping it up, which means I'm only covering what's on the outside. So if you think about it, if I take this cylinder, technically this cylinder has a top as well as a bottom, right? But what part am I not going to have to count? So we're not we're not counting the inside, but if I like take this cylinder out, what part doesn't count? The bottom counts because I can wrap the bottom. What part of it do I not wrap? The insides, but that's already given. What Tyrone said is that's what's true. We're not going to be wrapping up the top part because the top part up here is attached to the bottom of my hemisphere. So same thing with the hemisphere. The hemisphere is also a 3D figure that goes right on top, but we're not going to be counting the bottom of it, okay? So that part, when we calculate the surface area, we don't count either the bottom of the hemisphere or the top of the cylinder. Does that make sense? Cool. Okay, so we have my hemisphere and we have my cylinder. Now, what is the formula? We wrote this down yesterday. What's the formula for the surface area of a full sphere? What would be the surface area of just a normal sphere? Good. 4 pi r squared. So for a hemisphere, what would it be? Two pi r squared. Yeah, exactly. Now here's the question. Let's see who can get this. Does the 2 pi r squared count the bottom portion, or does it not count the bottom portion? Good, it does not count the bottom portion. So that's all we need, 2 pi r squared. And that'll be pretty simple once we have the numbers. Now for the cylinder, we're doing one of the circles plus the lateral area. Remember, lateral area is the side. Lateral area. And then the base of just the bottom, the base area. What would be the formula for the base area of my cylinder? What type of shape is it, and what would be the formula? Two pi r would be the circumference. What would be the area of the base? There we go, pi r squared. So the base is pi r squared, and then who remembers what's the formula for the lateral area? The lateral area. Remember, it has a height. This should be somewhere in your notes. We took them yesterday. It's in the list we made at the end of yesterday's class. It's all there. What is the lateral area for a cylinder? Break it down if you don't remember. What type of shape does it make? What's the area of that shape? Pi r L, that's for a cone. Or we don't have a cone, we have a cylinder. So Perla's saying length times width, but rather than writing L and W, I'm going to write what the length actually is and what that width actually is, because it's wrapped around a circle. We could go back. If anyone wants me to go back, I'll go back, but everybody should have had this written down already, so I shouldn't need to go back. All right, we're going back. No, it wasn't here. Where was it? Okay, here it is. We wrote it down. Lateral area, 2 pi RH. Yes, you were right. You were right, 2 pi RH. And this comes from the fact that the cylinder, if you take off, think of a can of beans. If you take off the wrapping of a can of beans, you get a rectangle where the height is h and the length of it is 2 pi r. Because the length wraps around the circle and makes the circumference of the circle. So the lateral area for a cylinder, 2 pi RH. And again, guys, this is something that we have to start trying to memorize and understand where it comes from as well. So does anyone have any questions on where this comes from? 2 pi RH. Okay. So back to here. The lateral area is going to be 2 pi RH. So altogether, we have 2 pi r squared plus pi r squared plus 2 pi r h. Does anyone have any questions on that? Okay. So now we can go ahead and fill in the blanks and add it all up. So the surface area, the total surface area is going to be 2 pi r squared plus pi r squared plus 2 pi r h. Now I have 2 pi r squared plus another pi r squared. So what can I write? Three pi r squared plus 2 pi r h. And at this point, we can pretty much fill in the blanks and do the math. So 3 pi, what's the radius? Go ahead, go back into the problem and let's read it actually. The height is 30. The diameter is 24. So what's the radius? 12. And the height is 30. Here's all the numbers. Go ahead, fill it in. And let's see what we get. All right. So 12 squared, 144, 144 times 3. What do I get here? $432 pi. And then 30 times 12, I get 360. 360 times 2, get 720 pi. So 720 plus 432. The surface area is going to be 1,152 pi. What are my units? Inches. Inches what? Squared. Good. All right, so what we're going to be doing for the first half of this class is we're gonna actually continue with this type of problem where you have a composite figure, and every time you have a composite figure, you really need to break it down and figure out, okay, what is being covered, what do I need to, which formulas am I gonna use, put it all together, and then that's how we're gonna work out each problem. So does anyone have any questions on this first one? Okay. All right. So let's go ahead and try a different one. So what do I have here? Just describe, let's describe what I've got. I have a rectangular prism and a hemisphere. Good. Now, here's something that we have to consider. Let me take this rectangular prism and draw it out real quick. When I take this rectangular prism and I take it out, I'm going to be calculating, good. I'm going to be calculating the surface area except for this circle right here in the middle. Because the hemisphere is sitting on top of it. Ooh, okay, that's a really good way to describe it. It's basically there's a hole in it because this hemisphere is placed right on top of it, and we're not going to be covering. If you were wrapping this in wrapping paper, you would not be covering the part underneath the hemisphere. So this part we have to take away from the surface area of this rectangular prism. So that, by the way, that has a radius of 3 units. So I'm going to be doing the surface area of the rectangular prism. I'll put SAR for rectangular prism minus what? But not just the hemisphere, but if I'm isolating just this part, just what's right here, that's the rectangular prism minus the circle. Exactly. So we're subtracting the area of the circle. Does that make sense? Any questions on that part? Okay, so we're going to find the surface area of this prism and subtract just the area of that circle on top. Then what am I adding to that afterwards? So after I've done this, what am I going to have to add on top? The hemisphere goes on top. Exactly. So then I take the hemisphere separately, and we take the surface area of this hemisphere. which we know from the previous slide, what would be the formula for the surface area of the hemisphere? Two pi r, nope, that was for the cylinder. It'd be 2 pi r no, go back. We just did it. Hemisphere. Whoa, 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 whoa. Where are we getting all this 2 pi RH from? I don't see that. There's no cylinders in this problem. 2 pi RH is cylinder. 2 pi RH came from here, from the lateral area of a cylinder. There's no cylinders here, just my hemisphere. 2 pi r squared. This comes from the fact that if it was a full sphere, it would be 4 pi r squared. But since it's only half of one, it's 2 pi r squared. So let's summarize what we're doing. We're finding the surface area of this rectangular prism, but then we're taking away the area of the circle on top. And then once we get that, we're going to add the surface area of my hemisphere. So let's go ahead and figure out, starting with the surface area of the rectangular prism. What is that? What's the formula for that? Rectangular prism. Good. 2 times LH plus WH plus LW. And then what's the formula for area of a circle? Pi r squared. Cool. So all together now, the total surface area, rectangular prism, was that supposed to be LW? No, yeah. Okay, I did it in a different order, but it's the same thing. So rectangular prism minus the circle, so minus pi r squared, plus 2 pi r squared. Cool. Is there anything I can simplify? Yeah. So negative pi r squared plus 2 pi r squared is just pi r squared. So 2 times LW, WH, LH plus pi r squared. Now we can fill everything in. Length is 10, width is 7, height is 4. So 10 times 7, 70. 7 times 4, 7 times 4, there you go, 28. Length times width, or length times height, 10 times 4, 40. And then the radius is 3. Okay, go ahead, go from here. Let's make sure we all get the same answer. Go ahead. So be careful when you combine like terms, because we're leaving it in terms of pi. And if one has it and the other one doesn't, treat it like a variable. You can't combine them. And we're adding, don't forget, we're adding, not subtracting. All right, so here, 70 plus 28 plus 40 times 2, you should get 276. Yes, so times 2, Tyrone, 276. Cool. So you get 276. And then 3 to the power of 2 is 9, so 9 pi. And what I was saying to answer Perla's question, can you combine these? Are these like terms? No, they're not. So we can actually, if we're leaving it in terms of pi, that's all we can do. We have to leave it like that. But if you wanted to round it, then you would go one step further. What's 9 times 3.14? Nine times 3.14, you should get 28.26. And then you would be able to add those together. So if you don't leave it in terms of pi, and I'm adding 276, you get 304.26 centimeters squared. So if you're leaving it in terms of pi, you can't combine like terms. But if you evaluate it by using 3.14, then you can get your final answer. So any questions on this one? Okay, someone remind me, why did I subtract the area of the circle? I want to hear you guys explain it in your own words. Because I'm not counting that. Okay. Good. We don't count it because you can think of it kind of like if this is like a hole that's in there. Okay, so you don't count that, but you do count the actual hemisphere on top. Yeah. All right, let's do another one. So we have, okay, a table lamp is made of a cone whose base is mounted on top of a cylinder. The diameter of the cylinder is 40 centimeters and its height is 10 centimeters. The cone has a slant height of 30 centimeters. What's the total surface area of the lamp? Okay. So Tyrone is saying we don't count the top of the cylinder. Good. What else do we not count? The bottom of the cone. Good. So where these two meet, we don't count that part. Because if you think about it, that's kind of like inside the lamp. So we don't count that part. Make this a little better. We're not counting that. And then for the cone, we're not counting the bottom. So this is kind of similar to the first one we did. Hold on. Okay, kind of similar to the first one we did. Let's break it down. So in my cylinder, I am going to be calculating the lateral height, the lateral area. So the outer portion, the sides, plus how many bases. Am I counting both bases or just one? Just one. So the surface area of the cylinder is going to be the lateral area plus one base. Now for the cone, I'm doing the lateral area am I doing the base area at all? No. So for the cone, it's just the lateral area. Just the side, not the bottom. So back to the cylinder. What's the formula for lateral area? Now this time you should have it because we just did it. 2 pi RH, good. So it's 2 pi RH. How about the base area? Pi r squared. Good, the area of the circle. And then you might have to look back in your notes, but what's the area, the lateral area? Just the lateral area of a cone. Yeah, good, Tyrone. Pi RL. So altogether, the total surface area will be 2 pi RH plus pi r squared plus pi RL. Can I simplify this at all? Can I factor anything out? Yeah, what do all three of those terms have in common? R and pi. Good. Let me make this a little smaller so I can fit it. All of them have R and pi, so I'm going to factor it out. I'm left with 2H. I'm left with R. And I'm left with L. Now we can fill in all of our blanks. What's the radius? Good, 20. Oh, my bad. What's the height? Ten. Radius, like we said, that's 20. And what's the slant height? 30. Good. All right, go ahead. Figure it out. Let's see if we get the same answer. Berla got 1400 pi. So we got 20. And then here I have 20 plus 20, that's 40. 40 plus 30, that's 70. And then yes, 20 times 70 gives me 1400. So I have 1400 pi centimeters squared. So do you guys, are we getting kind of the hang of it? We always, every time, kind of take the shape apart, figure out what does count and what doesn't count. Go back to your formulas that we wrote down yesterday and pick out the formulas that you're going to use. And that's why it's really important to have all of those formulas written down so that you can keep referring to them as we go. But
Well,
the more
hello.
Hi, Daniel.
What is this?
How was your test, Daniel?
Long story.
All right.
I hate it.
Well, it's over, so that's good.
Yeah, I honestly think I did pretty. I know it's a strong word. That's why I'm using it.
You don't think you did very well?
I think I did meh. If
Meh.
I get like higher than a 3, I'll be
That would be
good.
good. That would be good.
If I get higher than a 4, I'd be happy.
Okay. Well,
Are
good
you
luck.
making houses?
Sort of. We're doing composite figures. So we're putting shapes together.
Oh no, I'm gonna suck at this.
That's okay. Well, we got a couple more examples to try out.
And the math test is soon, so I'm gonna have to
Yeah.
deal with this.
All right. Any remaining questions on this problem? Going once. Going twice. Okay. All right. Let's check this one out. What's going on here? So it's missing the bottom. But what's going on? Because take a look at, there's more going on to the picture. The triangle is pregnant, okay. Kind of, but when you're pregnant, it goes out. This isn't going out. Where's it going? It's going in. It's going in. Now think about this for a moment. Think about this shape. Pretend you're holding it in your hand and you're going to wrap it with wrapping paper. When you're wrapping it with wrapping paper, are you going to wrap this part of it? You don't think so? It is kind of like an inverted pregnancy. That's kind of a weird way to think about it, but also not wrong. But the thing is, guys, this part, even though it's concave, it's going in, it still counts as the outside because everything that's on the inside would be like inside. This is still technically on the outside. You would take your wrapping paper and you would wrap it around, and you would wrap it around not just the cone, but you would wrap it around this whole thing on the inside. That would all be covered, and then you would bring it out and cover the outside as well. So all of that would get covered in wrapping paper. So what do we have? Let's break it down. What is this made up of? A cone and a sphere. Hemisphere, good. So here's my hemisphere. Is there any part of this hemisphere that I'm not going to count? I'm not going to count the top. What do you mean the top? What's the top? Okay, that's the top. But okay, I know that this is weird. I don't know. I wish I had a way to like show this, but I don't think I do. I don't think I have a way, unfortunately. No, I don't. But okay, think of like a cup. Okay, just a cup or a bowl. Think about a bowl. Let's do that. Let's say that you are giving your cousin a bowl, like a really nice bowl for their birthday. I don't know. And you want to wrap it all the way because you know what happens is if you don't wrap it, or no, here, let's do this. Let's say you're moving somewhere, your family's moving, and you got to make sure that all of your plates and bowls and stuff, they don't get ruined when you package them. So what do people usually do? They wrap it in what? Saran wrap or like the brown foil, brown paper, newspaper, right? Just to make sure that it doesn't get ruined. Do you just wrap the outside of the bowl? Would you only wrap the outside? No, you wrap the inside as well. You want to cover the whole entire thing. So that think of it as that's exactly what's going on. Think that maybe this can be like some sort of weird like ice cream cone bowl situation. you want to make sure that you're wrapping the whole entire thing so that when you move, it's not going to get ruined. Does that make sense? It's hard, it might be a little bit hard to conceptualize it, but that's exactly what's going on in this example. So we're wrapping this hemisphere, the whole hemisphere, just on the inside of it. Rather than wrapping the outside of the hemisphere, we're wrapping the inside of the hemisphere. So what is the formula we're going to use for my hemisphere? What's the formula for hemisphere? Just 2 pi r? Good, squared. 2 pi r squared. Then I also have a cone, but the cone, what does it have? What's happening on the bottom? Kind of a donut. Am I counting that hole when I calculate the surface area? No. So we have the surface area of a cone minus the area of that circle on the inside. So there's kind of a lot more going on in this case. So the surface area is going to be the cone minus the circle. We get the whole entire cone minus the circle. Would it only be pi RL for the cone? No, because we're doing pi RL and the base, right? The cone is made up of the lateral area and the base area, but then we're taking away that circle. So there's a lot more going on in this one than we've done in the past, but let's go ahead and continue breaking it down. So for the surface area of the whole entire cone, what will it be? Go back to your notes. What's the surface area of the whole cone? Pi r squared plus pi RL. But then we're subtracting the circle. Now, does the circle have the same radius as the cone or a different radius? Good, different radius, because look at this, the radius of the cone. Here, let me take this circle out. Okay, the cone has a radius, look carefully, of 10, and the circle has a radius of 8. Do you see that? It's just because it's like a donut, right? So this hole is a little bit smaller than this one. So I'm going to call it R1 and R2. So R1 is the bigger circle, and then R2 will be the smaller circle. So we're subtracting pi R2 squared. Now, looking at our diagram, I can label a few things, but what do I know and what do I not know that I'm going to need? We know the radius, diameter. And we have the height, but what am I missing? We don't have the slant. So what I'm going to have to do real quick, find the slant. Okay. So this is my cone. I know the radius is 10. I know the height is 24, but I'm missing L. So what's the formula going to be? Mhm. Good. Pythagorean theorem. So 10 squared plus 24 squared equals L squared. Yeah, I named it L because it is the L, it's the slant height. Okay, so 100 plus, what's this? 576. So 676, the square root of 676 is 26. So L equals 26, cool. Now we have everything we need. L is 26, all right. So let's just do this one. Let's do this one first. Or do you guys want me to make one big formula, or should we just do each of them separately and then add them at the end? I don't mind either way. Do it separately. Okay. So pi r1 squared. So pi, we said the r1 is the cone radius, so that's 10 squared. L is 26. And then R2 is the smaller circle. So that's 8 squared. Okay, so that's 100 pi plus 260 pi minus 64 pi. What do I get? $96 pi? No. 296. There you go. That's the cone minus the circle. Now the sphere. What's the radius that I'm using in this one? That one's 8, so this is R2. What do I get here? $128, good. 128 pi. So surface area of the hemisphere, surface area of the cone minus the circle, put it all together. I'll do it up here. So it's going to be 296 pi minus 128 pi. What do I get? Oh, sorry, wait, I'm adding them, not subtracting them. Silly Miss Lopez. So what do we get? 424 millimeters squared. All right, so we've done a lot of different situations. How do we feel? Tell me in the chat. How do we feel? What's challenging about it? What do you feel good about? What do you think that you need to work on? Okay, you don't like the inside of the circle. But the inside is the same as the outside. You can think about it both ways. It really isn't though. Okay, I know what I'm gonna do. I'll be right back. Okay, I'm back. Everyone with me? Okay, we all here? Cool. I have a hat. I want to wrap this hat, and I'm just ignore this part of it. But let's say that I'm wrapping this whole outside portion of it with wrapping paper. Okay? Is that going to be the same, or is that going to be different if I invert it this way? Is that going to be the same amount of wrapping paper or a different amount of wrapping paper if I turn it inside out? It's the same, right? So it doesn't matter if my hemisphere is bulging out like it was in the previous example, where it was like kind of on top of the cake thingy. Doesn't matter if it's bulging out or if it's bulging in. This is concave. Concave is when something is going into something else. And then this is convex, which is what happens when you're bulging out. But either way, it's going to be the same exact surface area because I'm still covering the same amount of hat. You can also think about it like surface area could be like the fabric that makes up this hat. All of the fabric that I used to make this hat, just because I have it inside out, is that a different amount of fabric or the same amount of fabric when it's inside out? It's the same amount of fabric. So if that confuses you, hopefully it makes a little more sense when you actually visualize it. In the problem that we were just doing, just because that was concave, it was inside of the cone, it's the same amount of surface area as if it were the other way around. Does anyone have any questions on that? Does that help to visualize it? Okay, so let's talk about that hole real quick too. Because let me see if I can think of a way to explain that part. Well, basically, the hole is just there. I think you're overthinking it a little bit, but let me go back to the problem because that I can help explain by drawing it out a little bit. Okay, so let's talk about that hole situation because the hole is there because if I didn't have a hole, then all of this would be filled in. This would be like a wall or like a lid. And if there's a lid in the way, can I get this in? Can I magically push this through the lid out to the other side? No, right? So there has to be a hole inside of the cone because if you don't have a hole, then you can't get the hemisphere to go through it. So if I don't have anything here, now I can take this, I can put it through, and then it's going to be where it needs to be. No, we're not. Yeah, no, we're not creating the hole. The hole is already there. We had to account for it in our calculations. Does that make a little more sense too? Okay. So there's our hole. There's the hemisphere. It's inverted it's inside out, but it still has the same surface area as if it were the other way around. Like if here, let's see if I can do this. Hold on. If I turn this around and put it this way, if it was bulging out instead, it would still have the same surface area. All the calculations would be exactly the same, and we would get the same answer. Okay, because the concave is going to be exactly the same as convex. Oops. So it's the same exact answer. Okay, now it doesn't want to turn the right way. It won't stay. I don't know why. Okay. Any other questions on this one? Okay. Let's do one more. So here's an interesting situation. We have something that's called a frustrum. And the reason I wanted to do this problem is because you might see that word on a test or something, but this is explaining what it is. So a frustrum of a cone is part of the cone with two parallel bases. So it's basically like a cone without the tippity top. If you guys can think of a traffic cone. Does a traffic cone actually have a tippity top? No, what happens at the top of a traffic cone? It's flat, right? It kind of has like a hole. So a traffic cone is actually not a cone. Technically, this is a traffic frustrum. Because a cone would go all the way to the top. It has to have an apex, but a frustrum is flat on the top. So it's like a cone with a flat top. That's what a frustrum is, which means that the bases of it are parallel to each other. So this is flat and this is flat, so they're parallel. Does anyone have questions on what a frustrum is? Okay. So a frustrum has its own special formula. So I just wanted to bring it up and we're going to add it to our list. Let me just look it up again because I just lost it. This is one that I haven't completely memorized either, but I have it written down. Okay. You guys are going to hate me for this one. All right, are you ready? It's long, but we're going to just write it down and then we're going to memorize it and that's it. You guys, some of you guys are really good at memorization. So this is your moment to shine if that's who you are. Okay, so the frustrum is made up of basically three parts, right? It has an upper circle, it has a lower circle, and then it has the lateral area. So there's basically like three parts to it. So the surface area is made up of the base, so the bottom, the top, and then everything around, which is my lateral area. Now, each of these is going to have a slightly different formula because what's wrong with the top and the bottom? Are they the same? They're not the same, right? They're different. So what happens is we have a bigger radius. So we're going to call this one capital R because it's bigger. And then we're going to have a smaller radius. So this one's going to be lowercase r. Then we also have a height, which is going to be h. And then 20 is my slant height. So we can call that L. Everyone with me so far? Any questions so far? Have I lost anybody? Okay, cool. And then Okay, so then the surface area of the base, we can do that on our own. That's just the area of the circle. So what would be the surface area, or sorry, what would be the area of the base using the letters we're using? What would be the area? It's a circle. It's just a circle, like any other cone. It's a circle. It's pi r squared, but we're using capital R. So pi r squared. What about the top? Perla, we are. That is a circle. The green, that's a circle. What did you think? Oh, no, we're getting to that. That's the lateral. That's lateral. We're getting to that at the end. Right now, we're just doing we did the base. Now the top is very similar, but the only difference is that we're not using capital R, we're going to use lowercase r. So pi r squared with a lowercase r. So that part is easy. This is the new information. The lateral area for a frustum. Are you guys ready? It's a little bit long. Okay, we good? It's going to be pi times r, lowercase r, uppercase r, times the slant height. It's not that bad. It's not that bad. Any questions on this one? Okay, well, now we have everything we need. Let's go ahead and fill it all in. Pi times the bigger radius, so it's 10. Pi times the smaller radius, that's 5. Pi times the sum of those, so 5 plus 10, times the slant height, which is 20. Put it all together and let me know what you get in the end.
Miss, is that supposed to be equal or is it supposed to be plus?
Oh, it's supposed to be plus, I'm sorry.
I accidentally unmuted myself.
That's okay. All right, Perla got 425. Anyone got anything different? I'll start breaking it down. So this is 100 pi, 25 pi, and then 15 times 20 It's 300, so 300 pi. So in total, I have, 425 centimeters squared. Questions? You do not need to quit. Y'all are not the same students that I thought you were. I thought you were a little bit stronger than this. Okay, so dramatic. So dramatic. All right, that was it for composite figures. So from here on out, remember, because there will be a quiz on Friday, like there always is. So if we can practice this as much as possible, I think what I'll do, because again, stupid Khan Academy just does not have good questions. I don't like the way that they're doing this chapter. So the questions that they have are just, I don't want to use them. But maybe like I'll post some practice problems on Teams so that you can practice before your quiz and you can ask me any questions you have, because this is something that will most likely be on it. So just be aware. So in the last 20 minutes, we're going to just quickly start on density. You've heard this word before, right? In your science classes? Oh, literally today. Wow. Well, that's amazing. Density is the amount of matter that an object has in a given unit of volume. So the formula that we know and love is right here. Density equals mass over volume. Oh, wait, really? That's so funny. Well, here we are today. We're doing it. Now, I really like to memorize this way, in case you forget. D equals M over V. The M and the V, they make a heart. So you can always remember, because we love density. D equals M over V. Questions on just the little formula? Okay, no questions. Cool. So let's go ahead and take a look at this example. Data about 2 approximately cylindrical wood logs is shown in the table. Determine which wood is denser. So we're trying to figure out which of these has a higher density. But in order to do that, we need to know, we know the mass, but we don't know the volume. But they tell us a big clue. They're telling us that this is approximately a cylinder. Now I have 2 different types. So let's draw 2 different cylinders. We have a Douglas fir, a fir tree. They're telling us that the diameter is 6 inches and the height is 17. And then we have redwood. And there's our diameter is 8 and our height is 12. Okay, let's place some bets. Who thinks that the fir tree is going to be more dense?
Me.
All right, Jalen. Anyone else?
Tyrone.
Perla. Perla's on team fir. Who's on team redwood?
Tyrone.
No? Tyrone, what team you
Pick a
on?
team.
Fir or redwood? Pick a team. Fir. Okay, we got most people on fir. I don't know, we'll see. Let's find out. So volume of a cylinder. What's the volume formula for a cylinder? It's been a minute. Volume of a cylinder. Yeah, it's not surface area anymore. We're switching back to volume. Pi r squared h, good. So volume pi times 6 squared times 17. What do we get? $612 pi. How about the redwood tree?
Can I switch teams?
No. What do we get? 768.
Wait, I have a question.
Yes.
Shouldn't it be 3 and 4 since that's the diameter and we're putting the radius?
You're totally right. I'm so sorry. Totally right. My bad. This should be 4. And this one should be 3. Go back and fix it. $153 pi and 192. Okay, now we're good. So Jalen, you want to switch teams?
Yeah.
You both want to switch? Okay. Now's your chance. Now or never. Are we switching?
Switch.
All right. So Jalen is now Team Redwood. How about Perla? No waiting. Go with your gut. What team are you on? Fur. Okay, you're staying on. Okay, let's find out. So now density equals mass over volume. So for my fir tree, the mass is 254. So I'm doing 254 divided by 153 pi. Well, let's actually do what's 153 times 3.14. So this is about 480.4. What do we got? When you divide, what do you get? Good, 0.53. That's the density of the fir tree. Now let's find out what the density is for my redwood tree. So 192 times 3.14, really quick. We get 602.9. So now density, mass is 271 over 602.9. What do we get? What do we get? What do we get? 271 divided by 602.9, 0.449. So 0.45. So which one's denser? Which one has a higher density?
I should still prefer.
You shouldn't have switched. Fur is the winner.
Yeah, corn cob.
Who's on redwood? I'm on redwood. I'm on fur.
So just because one is heavier than the other doesn't mean it's going to be denser, because the density depends not just on the mass, but also the volume. Okay, so since this, even though this one was lighter, it also had less volume, so it ended up being more dense. So that's the trick with density. You got to be careful. Any questions on how to calculate density? Okay. I'm gonna skip this one. Okay, this one's kind of fun. So actually, population density is pretty similar. For population density, it's the population over the area. So regular density is mass over volume, mass over volume. Population density is population over area. And that's basically the population density of something is basically saying, okay, how crowded is it in that place? So what do you guys think? Which city would have a higher population density? Miami or New York City? Which one has a higher population density? Which one's more crowded? New York City, exactly. Which city is going to have a higher population density? Miami or Wichita, Kansas? Miami. Wichita, Kansas, probably not going to be that crowded. So population density is basically measuring how crowded a place would be. Now let's take a look at this problem. Greenland is the least densely populated country in the world, with a population of 57,714 and an area of 836,109 square miles. To the nearest hundredth, what is the population density of Greenland in people per square mile? So this is very, very simple. We already know the formula, population over area. So the population density. No, Greenland and Iceland are both cold. They're both, look, Iceland is right here, right next to it. So population is 57,714. The area is 836,109. And now we divide. What do we get? You rounded? Yeah, that looks about right, 0.07. Now the units, this is 57,714 what? Nope, go back and read. People. This is square miles. So this is 0.07 people per square mile. Population density. Now, by comparison, I'm going to quickly Google population density of Miami. Let's find out. Ooh, you guys want to know what it is? What are some guesses? If this is the population density of Greenland, what do you think is going to be? Give me an estimate for the population density of Miami. How many people per square mile? 57. Okay, that's lock your answer in. Perla's guess is 57. Whoever gets the closest, I'm going to give you, I'll bring you candy the next time I come to school. Who's going to get the closest? Perla says 57. No, don't look it up. Oh, but you locked your answer in, so that's your final answer. Tyrone, what's your guess? Jalen, what's your guess? Samaj, Emily, Eric, Rios, what are your guesses? Population density of Miami. How many people per square mile? Y'all are boring. Really? No one's guessing anything? You have 5 seconds. 5, 4, 3, 2, 1. Wow, what a boring class, y'all. Boring. The population density of Miami is 13,000 people per square mile. Technically, Perla was the closest. 13,000 people per square mile. That's the population density of Miami. Think about it. A square mile, that's like, it's pretty big. A square mile would be like, I don't know, from JDD to the bay, to Biscayne Bay, like, or to Biscayne Boulevard, from JDD to Biscayne, and then like down like 5 blocks. That would be like a square mile. And there's a lot of people who live in that square mile. 13,000 people could easily fit inside of that area. So 13,000 people per square mile, that's the population density. All right, 217. So that's pretty much all the time we got today. We'll pick up with the rest of this tomorrow. But in the meantime, did I give you guys homework? I don't remember. Is there something on Con? I don't remember if I ever put it up. I think I did. Let me check. If I already put it up, then you have homework. If I didn't put it up yet, then you're off the hook. I didn't put it up. Oh, I did. Ha. You have homework due on Friday. It's pretty easy though, I promise. It really isn't that bad. So just make sure that you take a look at it. It's due on Friday. It's been up since Monday, so I just forgot to tell you about it. But you should not have much of an issue with it. All right, that is all for today. Have a nice afternoon. Those of you who are testing tomorrow, good luck on your tests. Hopefully I'll see you. And yeah, see you tomorrow. Bye everyone.